Last time, George signed off with a promise, and I've been waiting to collect. He said, take our chain and alternate two kinds of atom, call them A and B, a deep well, then a shallow well, the diatomic chain. Out of that one change, our single band will split in two, and a true forbidden gap will open up between the halves. Here's why I've been impatient. This whole series has been a one-band show. We built the band, set it moving, filled it with a C, and every time silicon came up, we helped ourselves to something our chain has never once produced. A gap, a forbidden stretch of energy above a full band. The modern world runs on that gap, and we've been living on credit. Today we pay it back, right?
Today we pay it back, and gladly. The gap is where this subject stops being about metals and becomes about everything else. A metal is alive at its shoreline, where full seats and empty seats sit a whisker apart. A semiconductor is alive because of its gap. The chip in your pocket works because a band filled to the brim has a forbidden stretch of energy above it. And we've only ever pointed at that structure from a distance. So here's today's contract. One change, alternate deep wells and shallow wells, and we'll watch the band split in two, see what a gap is made of, and in this model even get its size, the difference between the two well depths. And when we pour the electrons back in, the chain will come out born an insulator.
Then paint me the new chain, picture before machinery. I'm imagining a necklace with two kinds of beads that strictly alternate, A, B, forever. Is that it?
That's it. And let's give the beads their physics. The spacing is the same as ever. Every atom sits one lattice spacing A from its neighbors. And so is the hopping. One amplitude T for leaking between any adjacent pair. What alternates is the well depth. The A atoms are deep wells. An electron parked there has a low on-site energy, E sub A. The B atoms are shallow. Parking there costs more, E sub B. Cheap seats and dear seats interleaved down the whole chain. And notice what the repeating unit has become. Not one atom anymore, but the pair, 1A plus 1B, the unit cell. The chain is one cell, stamped over and over. Or if you like, two interleaved sub-lattices. The family of all the A's threaded through the family of all the B's.
Let me flag the bookkeeping before it bites us. In the earlier episodes, N counted atoms. If I say N today, I should mean cells, and the atom count is then twice N. But there's a bigger worry underneath. Our whole twist and zone story rested on one sentence. Slide the chain by one site and nothing changes. That sentence just died. Slide this chain by one atom and every deep well lands on a shallow one.
Both flags are right, so let's plant them properly. Yes, from here on, N counts unit cells, and the chain has twice N atoms. Hold that shift, it decides the ending of this episode. And yes, the old symmetry is gone, but a coarser one survives. Slide the chain by one full cell, by twice the atom spacing, and it lands on itself, deep on deep, shallow on shallow. So Bloch's logic runs as before, with a longer stride. States of definite energy pick up one fixed twist per cell, not per atom.
One twist per cell, not per atom. Then the window of twists, the zone, has to change size too, doesn't it?
It does. Remember where the Brillouin zone came from. Twists that differ by 2 pi over the repeat distance are the same state. So K only means something inside a window of that width. The repeat distance just doubled, so the window shrinks by half. The zone now runs from minus pi over twice the atom spacing to plus pi over twice the atom spacing, and its edge is where K times the cell length equals pi. Doubling the cell halves the zone.
Hold on, that should bother everyone who remembers the first episode's head count. We proved N sites means N twist states, nothing lost, nothing double counted. The two languages had to be the same size. Now you've halved the window of twists. Half my states just vanished. Where did they go?
They didn't vanish. They moved upstairs, and this is the first glimpse of today's punchline. Run the count in the new language. A ring of n cells gives exactly n allowed twists inside the halved zone. Same comb argument as the first episode, 1 tooth per repeating unit. But the chain has twice n atoms, so we need twice n states in total. So there must be 2 states for every twist at different energies. 2 bands, stacked one above the other. The outer half of the old zone folds up and becomes a second band over the first. Near the end I'll show you that folding explicitly. But I'd rather not pull 2 bands out of bookkeeping alone. I want you to feel where they come from. So let's shrink the problem down to its molecule.
The warm-up then. Strip the chain to just 2 wells and 1 electron, which is basically the hydrogen molecule's ion, isn't it? 1 electron shared between 2 protons, 2 wells side by side.
That's the picture, and it carries today's whole soul. 2 wells, 1 electron, and to start, let's make the wells identical. Depth E0 each, like our old chain, with the usual hop, minus T, connecting them. The electron state is 2 amplitudes, 1 on the left well, 1 on the right. Now, guided by the first episode, let me offer 2 candidate states. Candidate 1, the in-phase combination, ket left plus ket right, both arrows aligned. Candidate 2, the out-of-phase combination, ket left minus ket right, arrows opposed. My claim is that these 2 are the states of definite energy. Don't take it on faith. Let's check the first one right now.
Let me do it, it's small enough. The Hamiltonian on ket left gives E0 times ket left minus T times ket right, the sitting cost plus the leak to the neighbour. Acting on ket right gives E0 times ket right minus T times ket left. Add the lines and collect. E0 times the sum minus T times the sum. The whole thing is E0 minus T times ket left plus ket right. It came back as itself, scaled by a number.
Which is the definition of an eigenstate. You found a state of definite energy, E0 minus T. That's the in-phase combination, sitting below E0, the bonding state, the same physics as the minus sign we installed in the first episode. Amplitude shared in phase between neighbours piles up in the middle and lowers the energy. Run the same arithmetic on the difference and the hop flips its contribution. E0 plus T. That's the antibonding state, pushed above by exactly as much. Back then, I told you to keep bonding and antibonding in your pocket. Today, they're the main cast. And look at the shape of what happened. 1 atomic level, and the moment 2 wells could talk, it split in 2. Bonding below, antibonding above, separated by 2T. 2 wells, 2 levels, balanced like a seesaw. Hold that rhythm.
Now tilt the seesaw because our wells aren't identical. Make the left well deep, E sub D, cheaper, and the right shallow, E sub S, dearer. My instinct says the electron would rather live in the deep well. So what happens to those 2 tidy levels?
Your instinct is the answer, and the formula just dresses it up. With unequal wells, the 2 levels become the average of E sub D and E sub S, plus or minus the square root of half the well difference, that half difference squared, plus T squared. That's what solving the tilted molecule's little 2-equation eigenvalue problem hands you. The same crank we turned for the identical pair. And it's the general 2-level answer, so let's make it earn our trust at both ends. Switch the hopping off, T to 0, and the square root collapses to half the well difference. The levels are just E sub D and E sub S, the isolated wells, as it must be. Make the wells equal, and the square root collapses to T. E0 plus or minus T, our molecule from a moment ago. And notice, the square root is at least as big as either ingredient alone, so the levels sit farther apart than the bare wells would. Levels repel. Mixing lets the low state dig lower and shoves the high state higher.
And the lean? You said my instinct was the answer. Make it concrete. Where does the electron actually sit in each of those states?
Follow the T to 0 limit and let the hopping grow back in slowly. At 0 hopping, the low state is purely the deep well, the high state purely the shallow one. Turn on a small T and they mix, but continuously. The low state stays mostly on the deep well with a minority share on the shallow one, and the high state is its mirror, mostly shallow, a little deep. The low state leans deep, the high state leans shallow, and the lean's strength is a contest inside that square root. If the well difference dwarfs the hopping, the lean is nearly total, each state almost trapped in its own well. If the hopping dwarfs the difference, the lean nearly vanishes and you're back to the even-handed bonding and antibonding split. Keep that seesaw in your head. It's about to get stamped along an entire chain.
So here's the rhythm I'm holding. Two wells that talk give two levels. Bonding, leaning deep, antibonding, leaning shallow. And your promise is that a chain of such pairs turns each level into a band. Two bands. But a chain isn't one pair. Every A talks to a B on each side, pairs all the way down. Show me the machinery that tames that.
The machinery is the first episode's trick. Run one level up. Describe the electron cell by cell. In cell N, the state is two amplitudes. Alpha sub n on the A atom, beta sub n on the B. Down the chain, that's two infinite families of unknowns, coupled everywhere. But Bloch rescues us with the stride we agreed on. For a state of definite energy on a cell periodic chain, moving one cell over multiplies both amplitudes by the same fixed twist. E to the I k times the cell length. It's the motion episode's costume picture. The pair's inner shape repeats identically cell to cell, only the twist advances. So alpha sub n is a fixed alpha times the twist to the n, and beta sub n a fixed beta times the same. All the unknowns collapse onto one pair, alpha and beta, per value of k. The infinite chain becomes a two-amplitude problem, a molecule wearing a twist.
Then let me set up the equations, because I remember how this goes. Stand on one site and ask who lands there. I'll stand on the A atom of cell N. Its neighbours are both Bs, one on each side. But which cells do those two Bs belong to?
That's exactly the detail to slow down for. Fix the convention. Within a cell, the A sits first and its partner B just to its right. Then the B to the right of our A is in the same cell. It contributes minus T times beta sub n. But the B to the left is the partner of the previous A. It belongs to cell n-1, contributing minus T times beta sub n-1. So the A equation reads E sub A times alpha sub n minus T times beta sub n minus T times beta sub n-1 equals E times alpha sub n. And the B equation mirrors it. A B's neighbours are the A of its own cell and the A of the next cell over. E sub B times beta sub n minus T times alpha sub n minus T times alpha sub n plus 1 equals E times beta sub n.
Now the twist goes in, and if the first episode is any guide, the moment of truth is whether the cell index drops out. Beta sub n-1 is beta sub n times 1 backward twist. Alpha sub n plus 1 is alpha sub n times 1 forward twist. Substitute, and every term carries the same factor of twist to the n, which cancels off both sides.
And with that cancellation, n is gone, which, remember, is the test that our guess really is a state of definite energy. The same equation holds in every cell. What's left? E sub A times alpha minus T times the bracket 1 plus E to the minus I k times the cell length times beta equals E alpha, and E sub b times beta minus T times the bracket 1 plus e to the plus ik times the cell length times alpha equals E beta. Two equations, two unknowns, with K inside as a dial. For every twist in the zone, a 2x2 puzzle. And squint at its anatomy. Two on-site energies on the diagonal and a coupling connecting them. That's the tilted molecule, except the coupling isn't bare T anymore. It's T times that bracket, 1 plus a twist, because a B reaches its A partners along two roots, and the roots add like arrows.
Then everything hangs on the size of that bracket. 1 plus e to the minus ik times the cell length. And I can see it with the first episode's clock hands. It's the sum of two unit arrows, one frozen at angle 0 and one at minus the cell twist. When the twists are small, the two arrows nearly agree, and when the cell twist reaches pi, they're back to back. Walk me through the sum properly.
Two unit arrows, and symmetry does the work. They straddle their common bisector, half the cell twist on either side, so their off bisector parts cancel and their along bisector parts add. Each contributes the cosine of half the cell twist, so the sum has length 2 times that cosine. Only its length will matter for the energy. The arrow's overall direction is a bookkeeping angle we can absorb into beta. And half the cell twist is just k times the atom spacing, since the cell is twice the spacing. So there's the connector's strength, said slowly. 2t times the cosine of k times the atom spacing. At the zone center, k equals 0. Cosine is 1, the roots arrive perfectly in phase, coupling 2t, both hands pulling together. Marching outward, the roots drift out of step, and the coupling weakens. And at the zone edge, k times the cell length equals pi, so k times the atom spacing is half of pi, whose cosine is 0. The roots arrive perfectly out of phase and cancel. Dead. At the zone edge, the sublattices stop talking entirely.
Let me say the structure back because it's suddenly very clean. At every twist k, the electron's problem is exactly our tilted molecule. The deep well's E sub d becomes E sub a. The shallow one's E sub s becomes E sub b, coupled by a strength that the lattice dials, 2t cosine of Ka, full double strength at the zone center, fading to nothing at the zone edge. So I can reuse the molecule's answer at every k, average plus or minus that square root.
Reuse it, and you're holding the series first two-band dispersion. E of k equals the average of E sub a and E sub b, plus or minus the square root of half the well difference squared, plus the square of the coupling being 2t cosine of Ka. The minus branch is the lower band, bonding-like, leaning on the deep wells, the seesaw's cheap side stretched into a whole curve. The plus branch is the upper band, antibonding-like, leaning on the shallow wells. One formula, two curves, and every k in the halved zone carries one state of each. That's the two levels becoming two bands promise, kept. Now read the shape of it the way we always do. Walk k across the zone and watch the square root breathe.
I'll walk it. At the zone center, the coupling is at full double strength, so the square root is at its fattest. The two bands are pushed farthest apart, the lower one dipping to its very bottom, the upper one riding its very top. Marching toward the edge, the cosine shrinks, the square root thins, the bands lean in toward each other. So everything hinges on the edge. The coupling dies, the square root collapses to half the well difference, and the two energies are the average plus or minus half the difference. E sub b and E sub a themselves. They don't meet. The lower band climbs to E sub a and stops. The upper band comes down to E sub b and stops. And the daylight between them is E sub b minus E sub a, the well depth difference.
That's the gap. And you found it exactly where it lives, at the zone edge. The lower band tops out at E sub A, the deep well energy. The upper band bottoms out at E sub B, the shallow well energy. And the strip between them belongs to neither band at any K. No state in the entire crystal has an energy in that strip. That's a forbidden gap, the first this series has ever produced, and in this model, its size is exactly the well depth difference. One caveat said once, that tidy equality is a property of this alternating well nearest neighbor model. Real crystals set their gap by messier details. What generalizes is the location and the mechanism. A gap pried open at the zone boundary, which you shouldn't accept until you can see it physically, in a pair of standing waves.
Exactly. The gap just fell out of a square root, and I don't want to believe a square root, I want to believe an electron. You promise standing waves, two waves with the same wavelength but different energies. Show me the electron actually doing that.
Then stand at the zone edge. Recall the motion episode. At a zone edge, the electron's wavelength meets the reflection condition off the repeating pattern. Bragg reflection. A right-moving wave gets bounced into a left-moving one just as strongly, and the only patterns that can hold still are standing waves, crests and nodes nailed in place. At today's zone edge, the standing wave's wavelength is twice the cell length. Now ask what the old chain never faced. Where do the crests land? There are exactly two ways to drape that wave. Draping 1. All the weight on the A sublattice. Crest up on one deep well, crest down on the next, a node on every shallow well between. Draping 2. The mirror image. Weight on the shallow wells, nodes on every deep one. And that's precisely what the 2x2 predicted. At the zone edge, the connector died. The sublattices stopped talking, and the states became pure A and pure B. The algebra and the picture are the same fact.
So it's rent. The first draping lives entirely on the cheap, deep wells, so it pays the deep well rent. Its energy is E sub A, exactly. The second lives entirely on the dear shallow wells and pays E sub B. Same wavelength, same twist label, two different rents, and the gap is just the daylight between the rents. But forbidden is a strong word. Why is there truly nothing in between? Couldn't some clever wave split its weight and pay a rent halfway between?
It can split its weight, but it can't have a definite energy while doing it. At the zone edge, a blend of the two drapings isn't an eigenstate. It sloshes between the rents rather than paying one of its own. The definite energy menu at that wavelength has exactly two entries. Now sweep the zone to close the case. Walking K from center to edge, the lower band offers every energy from its bottom up to E sub A, the upper everything from E sub B up to its own ceiling. Between them, no twist anywhere offers a state in either band. It's not that those energies are expensive. The crystal has no wave to sell you there. That's what forbidden means. And run the logic on the old chain. Identical wells means the drapings pay identical rent. The daylight shrinks to nothing. The gap closes. That's why this series, with its identical atoms, never met one.
Wait, that last sentence hides a trap I want to spring deliberately. Suppose the atoms are identical, but I stubbornly insist on today's bookkeeping. I paint every other atom red, call the pairs cells, halve the zone, run the 2x2. Nothing physical changed, but the machinery hands me two bands. Two bands from a paint job? Was the single band picture of the earlier episodes wrong all along?
It wasn't wrong, and reconciling the two pictures is the folding I owed you. Describe the identical chain with a doubled cell and the outer half of the old cosine band, the twists beyond the new boundary, gets reflected back into the halved zone as a second branch. Why? By the new, coarser redundancy, twists differing by 2 pi over the cell length are now the same state, so a twist just past the new edge refiles as a twist just inside the opposite edge. The outer piece lands on top of the inner one. The band folds like a sheet of paper, creased at the new zone edge. So yes, two branches, but they touch at the crease exactly, because our gap formula with zero well difference gives both energies equal at the edge. Two bands meeting at a point is a single band wearing new filing labels. Nothing physical moved. Now turn on the well difference gently. The touching point is exactly where levels repel, and the AB difference pries the crossing apart into an avoided crossing. The crease opens into the gap. So the single band story was the special case of a closed gap. The diatomic chain doesn't overthrow it, it reveals it as one point on a dial.
The gap grows straight out of the paint, becoming real, beautiful. All right, we have the series' first true gap, and I know what this show does the moment it has bands. It pours in the sea, seats, exclusion, waterline. But the bookkeeping shifted under us, so set up the count cleanly before we pour.
Cleanly then. Last episode N counted sites, today N counts cells. Bend the N cells into a ring, and each band contains N allowed twists. One per cell, the same comb argument, now in the halved zone. Each twist is a bench with two spin seats, so each band holds two N electrons. Two N seats downstairs, two N upstairs. The ledger checks. Two bands of two N seats matches twice N atoms times two spins. Nothing lost in the halving, just reshelved.
Ledger balanced. Every state accounted for. Now pour.
Say each atom donates one electron, like the sodium story. Careful, that is not one electron per cell. Two atoms per cell, one electron each. Two per cell, so N cells hand us two N electrons. Fill from the bottom, seat by seat, and they exactly exhaust the two N seats of the lower band. Full to the brim. The upper band, empty.
Let me say that punchline back slowly, because it might be my favourite twist of the series. Last episode, 1 electron per atom was the recipe for a metal, sodium's half-filled band, a live shoreline. Today, 1 electron per atom again. The atoms are exactly as generous as before, and yet the lower band is exactly full, the upper exactly empty, and the waterline is stranded in the middle of the gap. Same donation, opposite destiny. The only thing that changed is that the repeating unit doubled.
That's the whole reveal. A full band is silent. That's the motion episode's theorem. Every eastbound electron cancelled by its westbound twin, and no gentle push can unbalance it, because the nearest empty seat is a whole gap away. And a waterline inside a gap is a waterline with no shoreline. The seat count at the waterline exactly 0. So the diatomic chain, with the most ordinary electron count in the world, is born an insulator. And here's the geometric rhyme. Last episode we parked the half-filled chain's Fermi points at plus and minus pi over twice the atom spacing. Today's zone edge sits at the very same spot. Of course, half-filling fills half the old zone, and doubling the cell halves the zone. They're the same half. The gap didn't open in some random corner. It opened precisely along the old shoreline, splitting the metal's busiest seats into a full floor below and an empty floor above.
Born an insulator. But that's clearly not a death sentence, or there'd be no silicon industry. And I've still got last episode's numbers in my pocket. Silicon's gap is a bit more than an electron volt, and room warmth deals thermal kicks of about 1/40th of an electron volt. So when the waterline lies inside a gap like that, what does warmth actually do?
Last episode, warmth blurred the waterline into a soft ramp within a band. Here the blur has to operate across a forbidden strip, and that changes its character. An electron can't be nudged upward in installments because there are no seats in the gap to stand on. It has to be splashed clear across in one lucky oversized kick. With the typical kick a small fraction of the gap, those splashes are rare, but not never, and each one that lands creates two carriers at once. A swimmer, alone in the empty upper band, and a bubble floating at the top of the full lower band. A few swimmers, a few bubbles, a trickle of conduction where the pure insulator had none. That trickle is a semiconductor. Diamond's gap of several electron volts makes the splash hopeless. A stubborn insulator. Silicon's modest gap makes it merely rare, and rare is workable. One scope caveat: real silicon isn't a line of atoms, it's a full crystal in space with a richer stack of bands. So our chain is the cleanest cartoon of the mechanism, not a portrait of silicon. But the mechanism is silicon's. A full band, a modest gap, a waterline inside it.
Now the trick that closed the motion episode gets its full setting. Doping: sprinkle in a few atoms with one electron to spare, or one too few. Back then it was a teaser about N-type and P-type. Today we own two bands. Give the trick its address.
The address is the two band edges bracketing the gap. Plant a donor, an atom carrying one spare electron. That spare goes looking for a seat, and the lower band has none. Every seat is taken. The cheapest seat in the building is at the bottom of the empty upper band, so that's where it parks. A swimmer made to order, no lucky splash required. N-type. Now plant an acceptor, an atom one electron short. That's one seat in the full lower band standing empty, and we know what an empty seat in a full C does. Neighbors keep dropping into it, and the vacancy floats up to the top of the full band and rides there as a bubble. Positive charge ready to drift. That's P-type. Swimmers at the floor of the upper band, bubbles at the ceiling of the lower one. Press an N-type region against a P-type region, and you've got the diode from the motion episode's close, now readable line by line on the band diagram.
Then let me cache the other souvenir from that episode, the diamond aside. Diamond's gap is several electron volts, and you said that's why it stays transparent, which sounded magical because transparency feels like a fact about surfaces and polish, not energy bookkeeping. Why does the gap decide what light passes through?
Because absorbing light is a seating event. A photon gets absorbed by lifting an electron from a filled seat to an empty one, and in our Born insulator, the cheapest lift on offer starts at the top of the full band and ends across the gap. Nothing in between exists. The gap has no seats, so you can't pay part of the fare. It's a ticket booth with one price: pay the full gap or ride through untouched. Diamond's ticket is several electron volts, and the photons of visible light carry less. No electron can take their energy, and the light streams through the crystal as if nobody were home. Transparency isn't polish. It's a gap too wide for light to pay. Silicon's ticket, a bit more than an electron volt, is cheap enough that visible photons pay it easily. They're absorbed within a whisper of the surface, which is why a wafer looks opaque and grey. A window and a chip, told apart by ticket price.
And the booth should run backwards, shouldn't it? We've got materials with swimmers upstairs and bubbles downstairs at the same time. What happens when a swimmer meets a bubble?
It falls. A swimmer at the floor of the upper band drops across the gap into a bubble at the ceiling of the lower one. Electron and vacancy annihilating into a full, quiet seat. And the fare it paid on the way down has to go somewhere, so it leaves as a photon, carrying almost exactly the gap. Run a current through the right semiconductor, keep feeding swimmers and bubbles into each other, and the material glows with the energy of its own gap. That's a light-emitting diode, the LED. Choose a material with the gap you want, and you've chosen the glow. We're staying qualitative today, but the principle is the booth running in reverse. Absorb by paying the ticket going up. Shine by collecting it coming down.
One more stop before the big picture, because this series keeps its lab promise. Is this thing buildable? Can the cold atom machines we keep visiting actually alternate deep and shallow wells on demand?
They can, and the trick has a name: the optical superlattice. Start with the crystal of laser light we keep visiting. Now overlay a second standing wave whose period is twice the first, lined up so its crests deepen every other well. The result is exactly our necklace: deep, shallow, deep, shallow. And the well depth difference is a laser knob. Start the knob at 0 and you've got the identical chain, one folded band touching at the crease. Turn it up and you can watch the gap open from nothing and widen as you dial. The avoided crossing performed live, atoms in the bands you choose. Everything we derived today, on a bench.
Then let me gather the whole arc, because I can finally see the shape of the series. We put one electron on a chain of identical wells, and hopping smeared its sharp level into a band, states labelled by a twist inside a zone. We read the band's shape, slope became velocity, curvature became mass, filling decided metal against insulator. Then exclusion poured in the crowd and built the Fermi Sea, the waterline, the busy shoreline, the silent deep. And today we doubled the heartbeat of the lattice. 2 atoms per cell meant 2 amplitudes, a 2x2 puzzle at every twist, 2 bands leaning on deep and shallow wells, and at the zone edge, 2 standing waves paying 2 different rents, with a forbidden gap of daylight between. Count the electrons, 1 per atom, 2 per cell, and the lower band fills exactly to the brim. The chain is born an insulator, or with a small gap, a semiconductor we can dope and light up.
And notice what that arc hands you as you walk out. The materials map, from counting. For any crystal, ask 2 questions. Electrons per cell against 2 seats per cell per band. Does the count land you partway up a band or exactly at the top of one? Partway, there's a shoreline, the gentlest push tilts the sea, a metal. Exactly full, then ask how wide the gap overhead is. Wide, several electron volts, an insulator, transparent and stubborn like diamond. Modest, a bit more than an electron volt like silicon, a semiconductor, alive with splashed and doped carriers. With the caveat from the motion episode, overlapping bands can turn an even count metallic anyway, the magnesium loophole. That's the periodic table of materials, sorted by a seat count and a ticket price. Everything on your desk is one of these answers.
Which leaves the one thing this series has kept frozen solid, the lattice itself. All along, the atoms have been bolted down wells, still scenery while the electron did all the living. But real atoms aren't bolted down, they can tremble, and I have a suspicion you've been saving that.
Saving it deliberately, because here's the wonderful secret. We already did today's mathematics for it. Unbolt the atoms and let them shiver, each one a mass tethered to its neighbours by springs. Ask how a ripple of trembling runs down that chain, and the very same structure we built today comes back. With 2 different atoms per cell, the vibrations organize into 2 branches. One slow and wavy, one fast and jittery. The 2-band story, reborn as sound. The quantum of that trembling has a name, and its next episode's title, the phonon. The lattice is about to sing.
That's a finale worth coming back for. Here's your homework image until then. Tonight you'll look through a window and past it maybe at a phone. The glass is clear because its ticket booth charges more than light can pay. And the chip inside the phone thinks because its gap is narrow and someone doped swimmers into one region and bubbles into the next. A pain and a processor. The same necklace of deep and shallow wells, read at 2 different gaps. Thanks, everyone. Come back next time and we'll let the lattice sing.